All right, so yeah, welcome back. I just wanted to maybe begin class by giving you a quick schedule or a quick overview of what the schedule will look like for the next 2 weeks, because as I've sort of said in class and as I've said in announcements, we are really getting near the end of the semester here. And in particular, we have a total of 5 class periods left. Monday, Wednesday, Friday, Monday, Wednesday, before the final day of classes. But we're really coming to an end of our brand new material in Calc2. And so what does that mean for the class? Well, we have a lot of time built in at the end of the semester for, I know, it's tragic, John. I'm sad too. We have a lot of room built into the end of the semester, specifically for some review, because in Calc2 we cover an incredibly wide range of material, and we do so relatively quickly. And I want to make sure that we have time to sort of pause and recap the stuff that we have learned, going out of this. So this is our schedule. Today we're discussing polar coordinates. It should be a ton of fun. And then sort of going forward, there will be a couple review days. On Wednesday, we'll review all of the recent stuff and or answer questions with regards to the practice test 3 that I sent out to you all in that email last night. So over the next 48 hours or so, I would encourage you to begin your studying for test 3, maybe try to answer some of those questions on the practice test and make note of the ones that you really struggle with. It is a-okay at the moment if you find that you're struggling with some of them, but it's a good time to make note of that so we have stuff to discuss on Wednesday. I probably won't prepare a ton going into Wednesday's class. Instead, if you send me emails with questions between today and Wednesday, I'll sort of know what to talk about, and or I can field questions on Wednesday. So, standard review session in the sense that I'll come loosely prepared, maybe with some example problems, but a lot of what I hope to talk about will just come from you all. Friday is test 3. There will be no class that day. And then the final 2 days of class, Monday and Wednesday, are a chance to just do some more general review. I've sort of potentially blocked off Monday for reviewing the early semester stuff. That was the like integration techniques and things like that. And then Wednesday for reviewing the middle semester stuff. So that was the sort of applications of integration, finding areas, finding volumes, all that fun stuff. Right, I mean, there's some question marks there in the sense that if you all have strong opinions about what you want to review, I'm happy to go with the flow, but unless I hear otherwise, that's sort of the idea that I've come up with. So any questions at the moment just about sort of either class structure for the final 2 weeks, end of semester stuff, anything there? Okay, great. Great. Well, in that case, let's jump into things. So today we're talking all about polar coordinates. Some of our goals include being able to describe points in the plane using either their rectangular or Cartesian coordinates or their polar coordinates, so being able to translate between the two. And I think we'll probably start there. Discuss some of the non-unique elements of polar coordinates, and this was done a little bit in the videos. And then something completely different, we are hoping to describe curves in the XY plane using polar coordinates. And we'll see some interesting examples of some curves going forward. So let's dive into it. One thing that I don't have a slide for, but that I want to sort of write up right away, were our polar coordinate to Cartesian coordinate transformations. So this was discussed in the video. These are good things to either to just remember or to be able to rederive. I often rederive them, so full disclosure, I really struggle to memorize these. But I remember that for a given point in the plane, we have sort of this picture, right? So maybe I'll draw my little XY axis here. I'll also switch to the bottom left corner. So for my XY axis, I've got a point in the plane that could be, maybe this point here. And it can be described using either polar coordinates, which describes an X value and a Y value, or it can be described using polar coordinates, which describe the radius, so the distance from the origin to the point in question, right? And so that was my radius r, or the angle that we get when we start at the positive x-axis and sort of rotate up until we're pointing directly at the point itself. So that's our theta. And so given the r and the theta, the picture that I always, sort of draw in the margins of whatever paper I'm working on are this. There's a triangle involved, right? And it goes from the origin out to the point. And then the triangle side lengths are x down here, y over here, r for the hypotenuse, and then this angle theta here. And from that picture in the margin, you can really rederive the translation functions or the equations that give us our transformations from cylindrical or from polar coordinates to Cartesian coordinates and back and forth. And so those are going to be given by, so we can calculate our x coordinate, right? Our x coordinate is just equal to r times the cosine of theta, right? And that's because we can think of that as SOHCAHTOA, right? So the cosine of theta will equal the adjacent side divided by the hypotenuse. So cosine of theta equals x divided by r, and so x equals r cosine theta. Similarly, we get y is equal to r sine theta. We get that r, the radius, is equal to, well, we can use the Pythagorean theorem for that. So r squared equals x squared plus y squared. So r is equal to root x squared plus y squared. And then theta is always sort of the odd one, as we saw last time. I like to think of theta in terms of tangent. And so the tangent of theta is equal to the opposite divided by the hypotenuse, adjacent, opposite divided by adjacent, right? So SOHCAHTOA, so tangent is opposite over adjacent. So tangent of theta is y over x. And so theta was equal to the arctangent of y over x. And then the final thing to keep in the back of your mind is that we possibly have to include this plus pi at the end, right? Because depending on the angle, the arctangent spits out angle values or theta values that are between pi over 2 and negative pi over 2. So just looking in the first and fourth quadrants, depending on where our point is, we might have to add an additional pi. And so these formulas are great to keep in the back of your mind. What I'll actually advocate for, though, and what I would encourage you to think about is to use these in conjunction with your sort of general geometric intuition and understanding of what's happening in the XY plane. So if we want to talk through an example, let's talk through an example. So I encourage you to use these formulas, but also to think about what's happening in the XY plane. And so I think this first example, all of the examples on problem 1 were asked to look at a given expression in polar coordinates and to convert to Cartesian coordinates. So polar coordinates, those are the r comma theta coordinates, and Cartesian coordinates, those are our x comma y coordinates. So polar coordinates, we're reading this as r equals 3 and theta equals pi over 2. So right away, we see an example of how we can either use the formulas directly or use some sort of geometric intuition and understanding. And it's really great to think about both of those as we go forward. So let me start with the geometric intuition. This is describing a point whose radius is r and whose angle is pi over 2. That means that when I go to graph this, I know that it's going to be 3 units away from the origin. But to calculate its angle, I'm going to start in the positive x direction and then rotate counterclockwise pi over 2 units. And pi over 2 is 90 degrees. So we're just going to rotate up to here. And so I know that whatever my point is, it's going to be a point that's been sort of rotated up pi over 2 units. And it's going to be floating somewhere up here with the total distance from the origin. So that distance there being equal to 3. And so just through my geometric intuition, I can recognize that this is on the y-axis. And so this has a coordinate of x equals 0. And because it's distance 3 from the origin, it has a coordinate of y equals 3. And so in Cartesian coordinates, right, in Cartesian coordinates, this is equal to the point 0, 3. Now, we could think about that in conjunction with our formulas down here, and I could explicitly have just calculated x equals 3 times the cosine of pi over 2, and that's 3 times 0, so that's just 0, and y equals 3 times the sine of pi over 2. So that's 3 times 1, so that's 3. So I could have just used these formulas and explicitly plugged in to get 0, 3. But we see that that's verified by our geometric understanding of this picture here. All right. And so that will ultimately come in handy as we work through these other problems, especially as we start to get to points either whose R value is listed as a negative number or whose angle is no longer in the first quadrant, but is in some other quadrant. Yeah, let me pause there. Any questions about this first example? Okay, well, let's keep going. I want to talk through, at least on this first page, I want to talk through all of these examples in kind of gory detail, though maybe we'll move a little faster than we did in this first example. In the second example, we've got, again, this is written in polar coordinates, so it's r equals 2 root 2, and then theta equals 3 pi over 4. And I want to, maybe even before I, well, let me do this. Let me go ahead and plot this point, again, using geometric intuition first. So I know 2 root 2, that's my radius. So I'm going to be 2 root 2 units away from the origin. My angle is 3 pi over 4. And so I have to remember what that is. 3 pi over 4 is going to be what we get when we sort of rotate up pi over 2, right? So that's 2 pi over 4, and then an additional pi over 4 after that. So it's going to be 3 pi over 4 is 90 degrees plus an additional 45 degrees. And so the point that I end up looking at is going to be the point that's out here. Or let me actually draw that. So because it was 45 degrees, I think that should be just a little bit further. I think it'll end up looking something like this. So this is the point in question, whose radius is 2 root 2, and whose angle is 3 pi over 4. Now, if we go to try to figure out exactly what that point is, I can again use triangles or similar, I can use a triangle over here to try to figure out what that is. And I could recognize this, if I so chose, as, say, this triangle, right? Which would have a 45-degree angle, a 45-degree angle, and a 90-degree angle. So I could start using, triangles and 45, 45, 90s to piece together what x and y are. Let me go ahead and use these formulas to help me out. And here we sort of see, I've leaned on the geometric intuition to gain a sense of where this point is, but I can now use the formulas to really drive this home. So my x-coordinate is going to equal, let's see, so that will be r times cosine of theta, so that's 2 root 2 times cosine of 3 pi over 4, and we'll get to what that is in just a second. And y is equal to 2 root 2 sine theta. So that's 2 root 2 sine of 3 pi over 4. And so by translating into these formulas, right, I can use this geometric intuition, but I also have to remember what my cosine of 3 pi over 4 is and what my sine of 3 pi over 4 is. And so thinking through that a little bit, we'll remember that that each of these involve the expression root 2 over 2, right? And specifically that sine, there we go, that sine of 3 pi over 4, that was root 2 over 2. And cosine of 3 pi over 4, that was negative root 2 over 2. And so when the dust settles, what we end up with is that our x-coordinate should ultimately be a negative. And let's see, the 2's will cancel, but we'll end up with a root 2 times root 2, so that's going to be negative 2. Our y-coordinate, the 2's will cancel, we'll end up with a root 2 times root 2, so that's positive 2. So in fact, we get that this point in Cartesian coordinates is given by x equals negative 2, y equals 2 in Cartesian coordinates. So again, we could have seen that explicitly using the triangle, right? And if we did that, we would have to create an appropriate triangle, in this case, a 45, 45, 90 triangle, and we would have to recognize that we're in the second quadrant, so our x value is negative. Or we could just refer to these formulas and remember what cosine of 3 pi over 4 and sine of 3 pi over 4 is. Either way, we get this as our Cartesian coordinate way to describe the point. Cool. So a second way to do this. And now for the third way, right, this final way, go ahead and do this. So this one has a negative r value, which is a little funky. So we have to remember how to deal with that. And again, starting with the geometric intuition, I can think of this as going up pi over 3 angle units, right? And pi over 3 was 60 degrees. So that's like 2/3 of the way up. And now if this was a positive one, I would go up in a positive 1 direction, and I would be right here. However, since it's a negative 1, I'll actually go in the same direction but flipped across the origin. So I'll actually come down in this direction 1 unit, and this is the point that I care about, right? So that was our convention when we have a negative r value. A negative r value means that we sort of draw it as we would with 1, and then we would flip it down across to become a distance negative 1, and so we would end up down here. So this becomes the point that we're actually interested in, and we have to figure out how we can describe that point. Again, we could use our formulas here, or we could use geometric intuition. Again, let's do both. And for geometric intuition in this problem, I might actually be interested first in figuring out what this point up here is, right? So this sort of blue point, I could note that that is the point given by, well, let's think through this. Geometrically, I have this, we said pi over 3 was 60 degrees, so I have this 30, 60, 90 triangle, right? And if I remember my 30, 60, 90 triangles, I might remember that if this hypotenuse is length 1, then the shortest side of a 30, 60, 90 is half the hypotenuse. And then the middle side is going to be whatever's left over from the Pythagorean theorem, right? So if our hypotenuse was 1 in this case, then the shortest length would have to be half that, so we get 1/2. And then 1/2 squared plus this thing squared equals 1 squared. So this side length was root 3 over 2. So we end up getting that our x-coordinate in this case would be 1/2. Right, and let me highlight that. So the x-coordinate in this case would be, I'll write it like this. I'll write x equals 1/2. And y in this case would equal root 3 over 2. But because we're looking at -1, right, we really want to focus on this point, we would have to flip that across the origin, meaning that each of these positive numbers would become a negative number. So we're not going positive 1/2 in the x and then positive √3/2 in the y. We would be going negative 1/2 in the x and negative √3/2 in the y. And so that value ends up being x equals negative 1/2 and y equals negative √3/2. And again, we could calculate that by plugging in r equals -1, theta equals pi/3 into these equations down here. So ultimately, I think these equations will help us. Having geometric intuition will help us, and being able to translate between the two viewpoints and verify that your computations are geometrically sound, I think is a really good skill to have. So here we have plotting sort of Cartesian coordinates given the corresponding polar coordinates. In a second, we're going to flip that and plot from Cartesian to polar. Maybe before we turn the page, any final questions about this? Okay, cool. Okay, let's go ahead. I'm going to keep the formulas down there. I'm going to erase a lot of the other stuff, which unfortunately just takes a moment. So we'll erase all of this stuff. We will keep those equations for the moment. And then we will go ahead and turn the page. Okay, great. Oh, look at that. So we actually want to see if we can do this. Just move that out of the way. Perfect. Okay. So now we want to take our Cartesian points, right? So again, this means that we're looking at a point where x is equal to the given point. In this case, x is equal to -1, y is equal to -√3. And then we are going to be asked to find polar coordinate representations. And here's where things get a little interesting. As we saw in the video, there are multiple ways that we can represent a polar coordinate, right? We can tweak the theta value, we can tweak the r value. So once we have a given point in Cartesian coordinates and we want to convert it into polar, there's not necessarily a unique way to do that. There's a standard way to do it. And the standard way to do it is to make our r value positive and to make our theta value be somewhere between 0 and 2 pi. Where I think if it's actually along the x-axis, we typically let theta equal 0 as opposed to 2 pi. Right? So theta is some number in between 0 and 2 pi, possibly being 0, maybe not being 2 pi. So that's our standard way to write a polar coordinate. Every point in the plane has a standard representation, except for the origin, but it is not the only one, so we can write it in other forms as well. And we see here we're asked to do that in a different form where our r value is negative. So let's give this a try. And here I might actually quickly talk through the first one, because I think it's very, very similar to our previous problem. Right? So if we want to take a look at this first one, we are looking at a point where the x value is given to be -1, and the y value is given to be -3. So if we were to graph -√3. So if we were to graph that, we would end up with the following. Right? X coordinate is -1, y coordinate is -√3. -√3 is something, it's like 1.7 or 1.8 or something. So we're going to end up with a point that's right around here, right? Where that distance, that's -√3, and that is -1. Okay, so once again, we have our formulas, and it's worth sort of trying to use the formulas here to see what we get. But then we want to use our geometric intuition to correct things if necessary. And what do I mean by that? Well, if I wanted to compute the r and theta value, I have my formulas, so I could compute r, in this case, would be the square root of -1 squared plus -√3 squared. So that's the square root of 1 plus 3. So that's just 2. So we get r is equal to 2, and theta is going to equal the inverse tangent, so arctan, of, and let's get the order here right, it would be -√3 divided by -1, possibly plus theta. So if we just compute this blindly, this is the same thing as arctangent of √3, which really means we're asking the question, what theta value gives us the tangent of theta equal to the square root of 3? And that's challenging to think about, right? Tangent, or really any of these sort of trig expressions is usually kind of challenging to think about. But if we think about it, the value that gives us tangent equal to the square root of 3 is going to be 60 degrees, or pi over 3. Right? We can think through that. That's, like I said, I think that's in and of itself pretty challenging, but we end up seeing that in order for the tangent of theta to equal pi over 3, we would need this side to be √3. We'd need this side to be 1. And again, we're in the world where we have a 30, 60, 90 triangle. And this angle here is the middle angle, so that would be 60 degrees, or pi over 3. So if we calculate this, this arctangent straight up, we get pi over 3 as our answer. And then there's a question of whether or not we have to include this plus pi. Right? And the answer here is yes, we absolutely do. Pi over 3 is an angle, it's 60 degrees. It's an angle here in the first quadrant. We have to sort of flip things around to get us down into the third quadrant. And so we will actually need to add that plus pi here. So the angle is going to be that arctangent plus pi, this arctangent plus pi, pi over 3 plus pi. And so we're going to end up with a representation of this point in which the r value is equal to 2, right? So we get r equals 2. And the theta value, right? Let me clear some space here. All right, so the theta value is going to be coming all the way around here. And that theta is going to equal not pi over 3, but pi over 3 plus pi, so 4 pi over 3. So we get r equals 2, theta equals 4 pi over 3. Okay, and that will be, like we said before, that will end up being our standard representation. I realize I should have written this in red to match the red underline here, but this will be our standard representation of this point in polar coordinates. However, we can also represent it with a negative r value, right? Or in any number of other ways, just by adding 2 pi to the angle. So I should say also, right, maybe green for this. Other ways that we can represent this point, we have r equals 2, theta equals, well, if I add 2 pi, that's adding 6 pi over 3. So theta equals 10 pi over 3. That's another representation of this same point, right? Visually, it represents the same radius r, but it represents sort of rotating all the way around the circle and then going an additional 4 pi over 3. So we get that representation, and we land at the same point. With a negative r value, and I should say there's a million different ways we can do this. So we have theta equals 10 pi over 3. We have r equals 2, theta equals 16 pi over 3. We have r equals 2, theta equals, let's see, if we went in the negative direction, we could do 4 pi over 3 minus 2 pi, so that would be a negative 2 pi over 3, right? That would correspond to going in this direction, going in the negative direction, 2 pi over 3. If we want to do the negative r value, we can represent this as r equals negative 2 and theta equals pi over 3, where it's just pi over 3. So again, that would give us, I'll draw this picture separately. This would give us the representation in which we're going up pi over 3. So we're going up our 60 degrees to get here, right? And that would be the point we had if r equals 2. But because r equals negative 2, we'll flip that to go in the opposite direction. So it'll end up coming down here. And we notice that that is actually giving us the exact same point that we've been discussing. So there are multiple ways to represent this single point here in polar coordinates, right? And yeah, this is a list of several of them. The boxed expression, this, is really the standard way to write it because our theta is between 0 and 2 pi and our r value is positive. But all of these are an accurate way to describe this point. Any questions about that? All right, cool. So the final thing that I want to say is that sometimes there is not like a nice translation in the sense that the numbers don't necessarily work out well. And this problem B is a great example. The point negative 2 comma 3 is a great easy point to write in Cartesian coordinates, right? In the Cartesian coordinate system, the point negative 2 comma 3, it's really easy to write. Here we go. We just go negative 2 units in the x direction. We go 3 units, positive 3 units in the y direction, and we're sort of floating up at that point right up there. That is to say, this point right here. Right? Great, nice, easy point to write in Cartesian coordinates. When it comes to polar coordinates, though, our formula does not work out nicely. And to just sort of highlight this, right? Visually, we see that we would have to figure out this distance, right? That r value, and then we would have to figure out sort of this theta value. So what theta is that? But if we try to use triangles, we realize that we don't have a nice memorized triangle in which one of the side lengths is 2 and the other side length is 3. Right? It's not a 45, 45, 90. It's not a 30, 60, 90. And so we might not have this triangle memorized. In fact, I definitely don't have this triangle memorized. And so our only path forward is to write out our r value and our theta value using the formulas. So in this case, r will equal the square root of 2 squared plus 3 squared, aka it'll be the square root of 13. And our theta value will be the arctangent of, and now let's think through this. Our y value was 3. Our x value is negative 2, so we get 3 over negative 2 as our arctangent. That'll give me some angle, and I don't have that angle memorized. Again, it's not going to be a 45-degree angle or a 30 or 60-degree angle. It'll be something weird. But because I'm in my second quadrant here, right, I know that whatever answer I get for this, I will need to add pi. Right? Again, I'll need to add pi if I'm in either the second quadrant or the third quadrant, because arctangent takes on values in the first and fourth quadrants. So even though this is sort of a messy formula, this is a correct formula. Just here I'm leaning a little bit more heavily on the formulaic representations because I don't have a nice triangle with nice sides memorized. So that's all I wanted to say about that second problem there. Any questions, concerns, comments at this point, just as far as translating back and forth? Okay, so for the rest of the class, I want to focus on graphing curves in the XY plane using polar coordinate equations. And I want to, maybe to motivate this a little bit, I'll make a little sidebar over here, right? To motivate this a little bit, I just want to point out that every equation, or maybe every curve, do I want to say it that way? I don't quite want to say it that way. I want to say it like this. Every time I have a relationship between my coordinates, or an equation that involves my different coordinates, I can often graph that as a curve in the plane, right? As a really, really simple example, using Cartesian coordinates, if I have the equation y equals 2, right? If I have the equation y equals 2, that's an equation. It's involving one of my coordinates, the y coordinate, but I know that y equals 2 corresponds to a horizontal line, pretend that's a flat line, corresponds to a horizontal line at height 2. If I want to get more complicated about it, I know, for example, that the equation x squared plus y squared equals 1. Let's say x squared plus y squared equals 4. X squared plus y squared equals, no, let's do 1. X squared plus y squared equals 1. That will describe a curve in the xy plane. It's a more challenging curve, but with a little bit of thought, we can recognize that it's the unit circle in the xy plane. And we've seen this a handful of times during the semester and possibly before that as well. But the equation x squared plus y squared equals 1 corresponds to this unit circle. Similarly, we can create equations involving polar coordinates, right? And they should also give us curves in the plane. So for example, we can create curves like r squared plus theta squared equals 1. We can create curves like r divided by theta equals 20. I'm just making these up as I go. And you can imagine that these will give us some curve in the xy plane or in the r theta plane, sort of describing the relationship between r and theta at that given point on the curve. It's worth examining this because it turns out that there are certain curves that are easier to represent in polar coordinates and some curves that are easier to represent in Cartesian coordinates. And I'll point out one example. It's actually this same example involving the unit circle, right? Earlier, we had that x squared plus y squared equals 1 was a way to represent that. But we know from our work in polar coordinates, and I'll take a little sidebar in this sidebar, we know in polar coordinates that if we calculate r, we have the relationship that r is equal to the square root of x squared plus y squared, aka we know that r squared is equal to x squared plus y squared, right? So if I go back up to my equation, originally I had written this as x squared plus y squared equals 1. I can write this in polar coordinates as r equals 1, or rather, I should say r squared equals 1, but because we have it as the number 1, right, I can take the square root of both sides and I will get r equals, well, let's say plus or minus 1. But, so I should say then, this equation, or rather this curve, this unit circle, is being described by the much simpler looking equation, r squared equals 1. And that makes sense intuitively if we think about r as being the distance from the origin. This is describing the set of all points whose r values are either a distance 1 or a distance -1 from the origin. But as we remember, polar coordinates, if our r value is negative, we just flip it across the origin. So it's either we're measuring it sort of like a distance 1 in this direction, or we flip it and imagine it as a distance 1 in the flip direction. Either way, we're measuring the set of all points that are distance 1 from the origin. And so it makes sense to describe this curve. You know, I think we can even drop the plus minus in r equals plus or minus 1. We can describe this circle using the much simpler equation r equals 1. So in short, there are certain curves that we might want to describe using polar coordinates. There are certain curves we might want to describe using Cartesian coordinates, or at minimum, it would be nice to examine some of these different possible values or several different possible curves to see what can happen. So that's going to be our goal for the rest of this class. On this page, we're going to examine the curves r equals c and the curves theta equals c. And these are sometimes called, in more advanced math classes, these are sometimes called the coordinate curves. Coordinate curves. Right, so we might be interested in when our different coordinates are equal to a constant. And again, we can think about what happens in the Cartesian case. We've already sort of given a preview of this, or we've said half of it already. But in the Cartesian case, we have two different curves we can think about. We can think about the curve like y equals a constant, and we said that that would just be a horizontal line occurring at the height of that constant. So y equals c is this horizontal line. The coordinate curve x equals c will be the same thing, but it'll be a vertical line. I would find the point corresponding to an x value of c, and it will just be that vertical line there. So the coordinate curves in Cartesian coordinates, x equals c and y equals c, correspond exactly to the sort of lines that you would imagine in a grid on a piece of graph paper, right? They're the lines corresponding to your different x values and your y values. What happens when we look at r equals c or theta equals c? So our coordinate curves in polar coordinates. Let's start, yikes, meant that to be a straight line. Let's start with r equals c. So here's my xy plane. If I want to draw r equals c, I could imagine what that is describing. R is the distance from the origin. So r equals c is going to be the set of all points that are the same distance from the origin, specifically distance c from the origin. So we've already seen r equals 1. We have, oops, meant for that to be a curvy line. R equals 1, we have the unit circle, right? This was our coordinate curve corresponding to the equation r equals 1. At the same time, if I had the equation r equals 2, that would correspond to the circle of radius 2, because every point on the circle of radius 2 is a point that is distance 2 from the origin. Right, so maybe I should be really, really explicit about that, right? The equation r equals 2 corresponds to the circle of radius 2, because that distance between the origin and any point on that circle is exactly 2. Right, and similarly, we can do this for all other colors as well, or all other radii as well, and I'll keep using different colors for that. So r equals 3 would be all of the points of distance 3, and so on and so on. R equals 1/2 would be the set of all points distance 1/2. Worth saying out loud, r equals 0. Again, 0 is always sort of the weird point in polar coordinates. It corresponds to the origin. And so r equals 0 would just be the single point at the origin itself. So that's r equals 0. Okay, but these are our coordinate curves in polar coordinates. At the same time, let's consider the second question. What about the coordinate curves corresponding to theta? So what if we choose theta to be a specific value? Well, again, I'll draw my xy plane here. Notice it's sort of weird. Every time I draw an xy plane, or every time I draw the plane, first of all, I have a hard time breaking the habit of calling it the xy plane. And secondly, I tend to draw the xy axes, even though I'm working in polar coordinates. I don't think that's necessary, but it's sort of, it's been like sort of ingrained in me, and it helps me visualize the plane in a more relatable format. So I don't think I had to draw these the XY axes, but it does help me sort of identify where the origin is, and it helps me think through these different coordinate curves. So yeah, you can take it or leave it. Let's take a look at some different theta values. Again, I'll probably graph several of these, and I will sort of color them differently and mark them differently. Let's start with theta equals 0. When theta equals 0, we are discussing the set of points in which I start in the positive x direction and I go up an angle of 0. I don't actually go up at all. And so it's going to be all of the points in which I go up an angle of 0. And so in this case, theta equals 0 will actually correspond to the x-axis. Now, there's an interesting question. Do I want to allow for negative r values? I think if I do, then this would include the negative x direction as well. So that's theta equals 0, but negative r values. If I don't want to include that, and to be honest, I don't think there's necessarily a standard way, but maybe we typically don't include the negative r values. So if I didn't want to do that, then it would just be the positive x direction, right, for positive r values. And so we end up with this ray emanating from the origin with angle 0. Maybe I'll make a note over here that we're going to just assume we're looking at positive or at least non-negative r values. Okay, and then I can graph any number of these coordinate curves. So r equals pi over 6, right? That's a 30-degree, or I'm sorry, theta equals pi over 6. That's a 30-degree angle. And the coordinate curve will correspond to that ray emanating out at that fixed angle. We can talk about theta equals, I mean, you get this. Now we can do this with any value of theta. So theta equals pi over 3. Theta equals pi over 2. Maybe I'll graph one more because they're so much fun. Theta equals pi over 2 can be coming up here, and so on and so on. Right, so every coordinate curve involving theta is a straight line sort of coming out of the origin, or a ray, I should say, coming out of the origin with the prescribed angle. So that's awesome, that's great. And once we can graph these sort of more basic quote unquote curves, right, these coordinate curves, we can think about how we might graph more complicated coordinate curves. And these will often require a little bit of thought. I mean, they all do, but slightly more thought than what we've had before. Typically, these involve sort of simplifying the equation down a little bit and noticing patterns and or plotting points and or using technology. So we will learn how to manipulate these both in terms of algebraic expressions. We'll learn how to manipulate these by plotting some points to see what they look like. We'll be able to, how are we doing on time? We're doing okay on time. We'll be able to plot this using, by converting into corresponding x and y coordinates, and we'll be able to plot this using technology. And I'd like to model all of those here in just a moment. So maybe first of all, let's take a look at this equation. This is the equation r squared minus 3r plus 2 equals 0. And the question is, what points in the plane does this correspond to? Well, I can treat this as I would, any other polynomial. I could try to factor this, and I can see what we get. And in particular, when I factor this, I get r minus, let's see if we do this right, we get r minus 2, r minus 1 equals 0. And so we get, in fact, two possible values of r. We get r equals 2 or r equals 1. I guess and or r equals 1. And so if I went to plot that in the xy plane, I would get that the curve corresponding to this equation, the quote unquote curve corresponding to this equation, is actually two different circles, right? It's the circle of radius 1 and the circle of radius 2. Cool, cool, cool. This one is a little bit trickier, right? So this one here, we've got r equals -3 cosine of theta. It's not immediately clear how we can go about simplifying that or solving that any further. So let me discuss two different strategies that we could employ for trying to figure out what coordinate curve this was. One is to plot points, right? And we've been doing this since we learned how to plot anything in the xy plane. I can plug in some theta values, figure out what the corresponding r value is, and plot that. And so let's do that for a couple of points, right? So if theta equals 0, whoops, get my pen back. If theta equals 0, then r equals -3 times cosine of 0. So that's just -3 times 1. So that's just -3. So when theta is equal to 0, r is equal to -3. And we're going to end up with this point. Let me go ahead and I'll mark off some points here. We're going to end up at the point where r is -3 when theta is 0. We're going to end up with this point right here. Next, if I plot another point, let's say theta equals, oh, I don't know, let's do pi over 4. If theta equals pi over 4, then r is going to equal -3 times cosine of pi over 4. All right, and then we have to think, cosine of pi over 4, well, let's see, that is √2 over 2. So this becomes -3 times √2 over 2. Okay, so that's a little challenging. Let's think through this. So we want to go up pi over 4 units, right? So here's pi over 4. And then we want to take our r value equal to -3 times √2 over 2. And so that will end up being, right, 3 over 2, that's 1.5. So this becomes basically 1.5 times √2, which is something like, 1.4. So we're going to end up sort of extending in this direction reasonably far. We'll probably end up right around there, I would think. Again, just sort of eyeballing this because I don't have a calculator in front of me. And then let me erase some of this, stuff that could messy up the picture. Let's plug in another point. Let's plug in the point theta equals, let's say pi over 2. If theta equals pi over 2, then r is going to equal -3 times cosine of pi over 2. Right, well, that's just -3 times 0, and so r is going to equal 0. And so actually, at pi over 2, we have r equals 0, and we are back here at the origin. Let's plug in one more point, and then we'll draw this to a close. When theta equals, let's say 3 pi over 4. Is that one we can compute quickly? If theta equals 3 pi over 4, r will equal -3 times cosine of 3 pi over 4. Cosine of 3 pi over 4, I want to say, is -√2 over 2. And so this would end up being a positive 3 times √2 over 2. In other words, the negative sign got canceled with a negative that appears in the cosine. So in this case, we're going over to this angle, and then we would extend positively. We wouldn't have to extend negatively anymore, so we'd end up with a point that kind of looks like it's up here. Okay, and then what do we typically do? We plot a couple points, and then we try to connect the dots in a way that's visually appealing. So I'll do that in just a moment. Well, maybe I'll do that now, and then we can consider erasing it. So a potential way that we could connect the dots is to draw something that kind of looks like this. That's not as visually appealing as I might have hoped, but that gives us a sense of what this picture looks like. Another thing that I can do is I can convert this back into Cartesian coordinates, right? XY coordinates, where I have a little bit more intuition sometimes. And so I want to point out, notice r is equal to the square root of x squared plus y squared. And cosine of theta actually isn't equal to anything. We have the equation x equals r cosine of theta. But that means that x divided by r equals cosine of theta. And that means what? That cosine of theta is equal to, so we have -3, and then cosine of theta will equal x divided by r, which is the square root of x squared plus y squared again. So we can actually simplify this in Cartesian coordinates to get x squared plus y squared. We take the square root and we multiply it up to the other side. Right, so we do that. So x squared plus y squared equals -3x. Right, and what does that equal? That equals x squared plus y squared plus 3x equals 0. And I think I should have chosen a number other than 3 here to make the numbers crunch out a little more evenly. But we can rewrite this if we want as x minus 3/2 squared plus y squared minus 9/4. Is that right? Equals 0. I'm possibly making a small mistake here. Oh, no. I think this is okay. So x squared, x minus 3/2 squared plus y squared equals 3/2 squared. So I should have chosen a number other than 3. This is making the numbers look a little ugly. But this, right, if we dig deep, this is equal to the equation of a circle centered at a point other than the origin. So in fact, what we're getting here is a circle centered at the point -3/2. Mistake. Yeah, mistake. This should be a plus here. That should be a plus there. So we're centered at -3/2. And our circle, if I had drawn this well, this should be a circle at that point. Awesome. So a more challenging example here, but an example in which we can begin to see how we might use polar coordinates to describe expressions and be able to translate in and out of those expressions. I should say in and out of Cartesian coordinates to possibly gain some insight into these expressions. The final, let me go ahead and stop sharing this. The final way that I want to point out that we can use technology, or the final way that we can graph these things, is to use technology. And so let me turn our attention over here. So hopefully you all can see this. You can see this expression or this website. So I've gone ahead and converted all of the equations in problem 4 into Cartesian coordinates. Basically, every time there was an r, I would replace it with a square root of x squared plus y squared. Every time there was a, I guess, cosine of theta or something like that, I would replace it with the corresponding x or y value. So I've converted all of those equations into Cartesian coordinates. Let's see what these curves actually give us. So our very first example, we actually get those 2 circles that we were expecting, which is awesome. Our second example, we get the circle centered at the point, there we go, centered at the point 1/2, -1.5, with radius 1.5. So we get that circle that we were hoping to see. The third and fourth example are a little weirder, and so I just wanted to put them out there to see what they look like to give you a sense of what's possible. This third example actually gives us this really weird figure 8, which we would only really be able to see, probably with our current skill set, if we plotted points kind of carefully and saw what happened as we traced around. So we get this interesting figure 8. And the fourth example is something called a cardioid, sort of classic example in polar coordinates. It kind of looks like a circle, but it has this little indent. And so it kind of takes on a heart shape, right? A little bit like a heart shape. And so it's often called the cardioid. And so those are some extra examples that we can graph using polar coordinates. Throw them all up there. Any questions at the moment about anything that we have here? That is cool. Yeah, I totally agree. I should say that this example, or examples of translating from Cartesian coordinates into polar coordinates, are one example of more advanced or different kinds of coordinate transformations. And it becomes more and more valuable as we go further in our math classes or in our applied math classes, like our physics classes, to be able to address a problem by translating into a coordinate system that makes more sense to us. Oh, I should point out, let me see if I remember how to do this. Desmos has a way, when you graph settings, you can either use your grid, which uses the Cartesian coordinate lines, or you can draw your polar coordinate lines on there as well. So this is actually probably the view that we should use when we're examining these kind of equations, right? So that's giving us the polar grid in which we have our coordinate lines corresponding to r equals a constant and corresponding to theta equals a constant. So that's kind of awesome. Okay, with the time that we have left, I want to actually pause. So I think I've said everything I need to say, and I want to turn to course evaluations. Let me go ahead and stop the recording.